Welcome to Intro to Constant Coefficient Homogeneous Systems. So let's consider a system of the form y prime is equal to a times y, where a is an n by n constant matrix. So in this case, as A is an n by n constant matrix, all of our coefficients are constants, and we are looking at a homogeneous system. Recall that when we are working with just single differential equations, with constant homogeneous differential linear equations with constant coefficients, we assumed that y was just e to the lambda t. Okay, so recall when we were solving homogeneous linear ODEs with constant coefficients, we assumed that y was equal to e to the lambda t and went from there. We are going to parallel this technique in systems. So we will use a similar technique with systems. So since our system, each solution itself is a vector with n functions, we can't just assume our solution is y equals e to the lambda t. We need a vector itself. So we will assume that the solution vector y is equal to some vector psi e to the lambda t. I'm using the Greek letter psi. You can use whatever symbol you want for that vector, and then multiplying e to the lambda t. So note that we would have y prime is simply equal to lambda times psi e to the lambda t. I should note here that psi is just a constant vector. So plugging into our equation, so plugging into y prime equals ay, we get that lambda times psi e to the lambda t is equal to a times psi times e to the lambda t. And so this means that lambda times psi must be equal to a times psi. Or in other words, we can rewrite this as a minus lambda times the n by n identity matrix. All multiplying psi should be equal to 0, the 0 vector. So if we want a non-trivial solution, which we do, so we want a non-trivial solution, so we need psi to not be the 0 vector. And so that means that a minus lambda times the identity matrix better be not be in invertible, right? So this means that A minus lambda times IN is not invertible. And so we have that the determinant of A minus lambda IN must be equal to 0. So the values of lambda that make this true are precisely the eigenvalues. So essentially we are finding the eigenvalues. Which will denote lambda I. Then furthermore, if A minus lambda I times IN times psi is equal to 0, I'm going to now name this psi I to partner with our lambda I. With psi I not equaling 0, then this means that our psi I is an eigenvector corresponding to eigenvalue lambda I. Keep my screen. So we get solutions yi equals psi I times e to the lambda I t. So we have a few cases. Note, if all eigenvalues are real valued, so if all eigenvalues lambda 1 through lambda n are real valued, and there are n linearly independent eigenvectors, psi 1 through psi n, where psi 1 or psi I corresponds to lambda I. Then y1 equaling psi 1 e to the lambda 1t through yn equaling psi n e to the lambda nt from a fundamental set of solutions. I apologize, my screen is not updating correctly. All right, we'll try this format. So we have y1 again equated to psi 1 e to the lambda 1t all the way up through yn equaling psi n e to the lambda nt. These solutions form a fundamental set of solutions. So we can show pretty easily the Wronskian evaluated at 0 would just be psi 1 as the first column The determinant of the matrix was Xi1 as the first column through Xin as the last column. And this has to be non-zero since Xi1 through Xin are linearly independent. So we, by default, have linearly independent solutions. It doesn't matter what the lambdas are, they can be repeated or not. We just need these n linearly independent eigenvectors. If we do not have all real value, or if we do not have n linearly independent eigenvectors, we get different cases. So if we have complex eigenvalues, or we don't have n linearly independent eigenvectors, things get a little more complicated. And we'll see these cases in sections 10.5 and 10.6. In 10.4, we will focus on the case where we have all real eigenvalues and we do have that basis of eigenvectors. In the next video, we'll do some examples, specifically with a 2x2 case, and then I'll do a video with the 3x3 case.